We have achieved great things. We have made giant leaps. We've gone far beyond what we thought was possible. But we have only just begun. Our future in space is unlimited, and it will benefit all humanity. But it will take hard work, new technologies, advanced financing models, and enabling public policy. The Beyond Earth Institute is creating a policy and legal framework to enable the creation of economically vibrant communities beyond Earth. We will engage all stakeholders on critical policy issues: property rights in space, norms of behavior, conflict resolution protocols, filling the technology gaps, exploring new financing mechanisms, and making space settlement an agreed goal of the U.S. and its allies. Beyond Earth is committed to the true purpose of why we go to space. Join us on this journey.
Good afternoon. I'm Courtney Stadd, Executive Vice President, Beyond Earth Institute. I'm filling in today for Steve Wolf, co-founder, president of BE, and he is today's moderator for this timely and compelling webinar regarding the potential of mining helium-3 on the moon. As you can see, BE has recruited an impressive panel of subject experts. Based on the registration for this webinar, many in our community clearly regard this topic as important regarding the nature and scope of the potential market-driven opportunities on our nearest celestial body. And a personal note, when I was a member of the White House National Space Council some decades ago, I recall the late Dr. Edward Teller coming to our offices and making a passionate case for the U.S. to take the lead in exploring the potential benefits of H3 on the moon. So I, for one, look forward to in the ensuing discussion regarding what advances have been made in the intervening years and how close are we to determining whether extracting H3 indeed represents a viable market opportunity. Okay, I now turn the microphone over to Steve.
Thank you so much, Courtney, and welcome everyone to this webinar today on helium-3. I'm super excited about this, so let's get into it. You know, it's been estimated that 1 ton, just 1 ton of helium-3 has the energy equivalent of 50 million barrels of oil with a dollar equivalent of $3.5 billion. As Courtney indicated, the promise of mining of helium-3 has been something of a holy grail for over 40 years among those who are interested in the development of space resources. Of course, this is linked closely to the maturation and operational fusion reactors that use helium-3 as fuel stock. Many in the space sector believe that if helium-3 can be efficiently harvested from lunar regolith and returned to Earth, that would be the single most important economic driver to justify lunar development. In just the past year, helium-3 has gained renewed interest as the requisite technologies for accessing and utilizing helium-3 seems to have been maturing at an ever-increasing rate. That's why the Beyond Earth Institute feels that this is an appropriate issue to give our attention to, and the fact that nearly 200 people have registered for this webinar is a very strong indication of the broad-based interest in this topic. I couldn't be more excited about the panel that we have gathered today and can't wait to hear from them. So let's get right into it and make introductions. First, I want to introduce Gerald Sanders, who has worked at NASA Johnson Space Center for over 37 years in the propulsion and power division of the engineering directorate and has extensive experience in propulsion, fluid systems, and in situ resource utilization, or ISRU. Mr. Saunders has worked in the area of ISRU for over 29 years. I should also note that when this video is posted, there will be a link to a set of slides that Jerry would like to share with you, so be on the lookout for that. Next is Dr. Ahmed Diallo. He's the program director at ARPA. That's the Department of Energy's Advanced Research Projects Agency for Energy, where he advances commercial fusion energy by guiding and overseeing transformative research projects. Before joining ARPA-E, Dr. Diallo worked at the Princeton Plasma Physics Laboratory for 13 years. Finally is Dr. Chris Salvino. As CEO of and Chief Engineer of Lunar Helium-3 mining, Dr. Salvino leads the mission to extract lunar helium-3 to return to Earth, powering the future fusion reactors and achieving the world's first green energy source. With a master's degree in aerospace engineering and flight test engineering from the National Test Pilot School, Chris brings hands-on expertise in aerospace systems and engineering environment. Now, I encourage you all, the resumes of these individuals are rather long and extensive, and I definitely encourage you to look them up and to read more about what they bring to the table and to this discussion. We'll first hear from Dr. Savino. He'll give us an overview presentation before we get into a conversation with the rest of the panel. Dr. Savino.
Sure. Can you hear me okay, Steve?
Sounds good.
Okay, thanks. So I want to kind of jump around a little bit today. I appreciate the panelists and the ability to talk today. I want to focus on helium-3 as the potential tip of the spear for a future lunar economy. Our company is singular focused on the extraction of helium-3 for nuclear fusion reactors, which Ahmed talked about, and quantum computing, which I'm going to talk about in a minute. My background is which Steve has mentioned already, but I want to point out that my interest in helium-3 came from an advanced degree in planetary geology. And once I obtained that, I didn't quite understand how we could mine it or how we can engineer it. So I added some additional educational background to try to understand this pretty cool opportunity. So I'm going to cover a bunch of cases fairly quickly, or a bunch of things on the agenda. And the most important thing is I want to go through the use cases briefly, a little bit about sourcing, and then the challenges of mining, and two particular challenges in detail. So the helium-3 does come from the solar wind. You might wonder why we can't get it on Earth. It's captured in our atmosphere, so you cannot obtain it on Earth. But on the moon, there's no atmosphere, so it's baked into the moon for the past 4.5 billion years. The question is, and it's a really important question, is there different areas of the moon with different concentrations? No one has a perfect answer. Here's some hypothesis. It comes from the solar wind. The equator has been pointed at the sun for 4 billion years, so it's probably more concentrated at the equator. The highlands are older, so maybe it's more concentrated there, but the Maria contain aluminite, which may better retain helium-3. 4 to 4.5 billion years ago, there's a ton of impacts into the moon, which is called lunar gardening. And back then, the ground was turned over dramatically, but the past couple billion years, it's been pretty quiescent for the most part. So more of the helium-3 actually may be at the surface. There's three ways we hypothesize on how helium-3 could be actually in the ground. One is through the solar wind and its interstitial amongst the regolith grains. One is from impacts from meteorites. Because of the energy impact and the temperature impact, they could be embedded in minerals. China came back with a great sample showing that it was in a mineral, and they termed that mineral Changstein. It's also possible that helium-3 is attached to chemicals such as aluminite. So there's three different ways potentially helium-3 could be in the regolith. It's possible all three of these come into play. Question is why we're going to go back to the moon. Politically, we might, or publicly, we're probably going back for research, potentially competition with China to prepare for a Mars mission. But I would argue that extraction and bringing this valuable resource back may be a positive return on investment. Ahmed's gone through the use case for helium-3 on nuclear fusion. I am going to skip that except for one particular slide. It's this one, and I want to add to what Ahmed said. Nuclear fusion, what we call 1.0, we coined that term, is with tritium. That's because it's really the only resource, the main resource they can get that combines with deuterium. If you can have nuclear fusion 2.0 with helium-3, there's a bunch of advantages here. It does not require long-term containment of byproducts. As Ahmed mentioned, it's less reactive because there's protons, not neutrons, less dangerous for humans, and a slightly higher energy yield. So to me, if we have fusion with helium-3, that's going to be the world's first large source green energy. The average fusion reactor is going to need about 20 or 200 kilograms of helium-3 per year. If you extrapolate all energy across the world being powered by fusion, it comes out to about 570 metric tons of helium-3 per year. That may sound like a lot, but as Steve mentioned earlier, compared to coal, if you had to do this with coal, that's in the billions of tons of coal to power electricity. The second use case, though, which is also a really important one, strategically maybe important than helium-3, is quantum computing. So quantum computing, while still experimental, is expanding rapidly. It's extremely fast. Here's a great example. If you had a string of characters that are 2048 in length, if you used a classical computer to break it down into its prime components, it would take 10,000 years to compute, whereas a quantum computer could do this in 8 hours. The applications are mind-boggling, from cryptography to drug discovery to potentially weapons production. And what does this have to do with helium-3? Well, the quantum computers, in order to work, have to be cooled down to near absolute Kelvin, near 0.01. And the only way to do that presently is with a combination of helium-3 and helium-4. In fact, each quantum computer is going to need about roughly 1 to 10 liters of liquid helium-3 for cooling over their lifetime. No one really knows how many quantum computers might be around, but we took a conservative estimate and suggested that if by 2040 we had 10,000 quantum computers, that would need about 4 metric tons of helium-3. So the amount of helium-3 needed for quantum computers is by far less than fusion, but the importance is probably more important than fusion to get going. Really brief about revenue. Today's helium-3 prices are roughly $30,000 a gram, or about $30 billion a metric ton. That's probably going to go up or down, probably would need to come down for fusion, but the numbers are fairly staggering. We're talking about a $1 trillion industry that's brand new to mine helium-3 and bring it back to Earth. On Earth, helium-3 only comes right now from a byproduct of weapons production. In fact, the United States used to have about 20 kilos. I don't have the actual number, but it's suggested that we only have about 10 kilos or less of helium-3 in the United States. So that means we then have to turn toward the surface of the moon, where there's an estimated 1 million tons. There's been very little really on advancement of helium-3 mining. There's been sample confirmation by US and China. Some governments, including China, are talking about permanently going back to the moon to mine helium-3, and probably also India. Our company and some other companies are beginning to look at the development of helium-3 mining on the moon. This, to me, is probably the most important slide I have up. The success of mining helium-3 is going to be when 3 things come together: the reduction in transportation costs, like we saw with reduction to low Earth orbit. Commercialization of fusion is right around the corner. But the most important thing to me of these 3, from our point of view, is we've got to actually come up with mining techniques that embrace the environment of the moon and don't use Earth-based techniques. This is a pretty famous gold mine in Australia, and all mines on Earth use basically a similar technique in which energy is used to extract ore. It goes through a processing plant. Out the back end comes something called tailings, which is wasted rock, and then the valuable resource is retained. There's a fair amount of energy in that extraction. That's that's a centralized process in Australia, but the concept is the same. There's a fair amount of energy to extract your resource. That's a pretty cool drawing of a proposed lunar miner. It doesn't belong to any one particular company. It uses the same process where there's energy involved in the front with that wheel to grind up the ground, to extract it, to bring it back inside and process it. You spit out tailings or wasted rock out the back end. So now I'm going to come up with the next couple slides. I'm almost done, but this is a really important one. This is a challenge. One of the challenges of mining helium-3 is the concentration is very small on the moon. It's estimated to be about 1 part per billion. So it's way less than an Earth-based copper mine or a gold mine. So if you use Earth-based mining techniques, you're going to use a fair amount of energy to extract 1 part of usable helium-3 from 999 million parts of unusable tailings. It's impractical, we believe, from an energy perspective. So the key to mining helium-3 on the moon is going to be to use a novel, low-energy extraction process that would not be seen on Earth. The second one, which Jerry or Ahmed has mentioned already, is that the dust on the moon is nothing like the dust on Earth. There's been no erosion, there's been no wind or water, so it's sharp, it's spickly, it's high in silica like glass, it's charged and it's magnetized. This creates a significant challenge. In fact, if you looked at the Apollo program and the lessons learned, Apollo 17 had about 3 EVAs totaling 22 hours, and it did a fair amount of damage. So the key to success for mining helium-3 is going to be to minimize the complexity and the number of moving parts to reduce mechanical failures. They're going to happen, so you have to minimize it and anticipate this. Just 1 or 2 slides about our company. When we decided to come together and produce a company to look at helium-3 extraction, the whole idea was to adapt to the moon's ecosystem. And this requires a collaboration amongst different disciplines because no one particular person understands the moon, and it's going to be a long time before we really do as a society. But I think it requires a diverse set of minds to actually come up with a way to hopefully strategically extract helium-3 from the moon. And I'll end on this slide about our company. Our company has been solely focused on this process of extracting, and if you look at the graphic, we live within 5 steps: targeting, heating, directing, collecting, and compressing. And with that, I will turn it back over to Stephen. Thank you for the time.
Excellent. Thank you. Thank you, Chris. And if we could bring everybody now into the room here, we could begin a conversation. You know, I've been watching the chat field, and I find it very interesting. This question of China. Let's just start with China as they're a competitor. So we know that the technology, maybe there's still a fair amount of maturation going on. And I guess this question is for Jerry. I know you don't work at headquarters, so this may not be the best question for you. But does the possibility of China and its ambitions for the moon, the lunar surface, and its statements on helium-3 impacting a sense of urgency about this area of ISRU at all, at least from your perspective?
And again, I think, Steve, you hit the nail on the head. While I work for headquarters in the role of ISRU capability lead, I am not involved or privy to those kind of conversations. I will say that any direction I have received from headquarters in STMD or ESTMD management has not relayed any level of urgency associated with China or any other international space agency for that matter.
And I mean, do we think that there's not the kind of urgency only because where really is the technology? Chris, I mean, it's so exciting to hear the prospects, but how soon do you think this is really all going to come together technologically before you think you'll be able to extract the first few pounds of helium-3 that will be brought back to Earth realistically from your perspective?
If you're asking me, our company's at a TRL level 2,
Hmm.
probably 3 fairly soon. And obviously, there's a few steps involved to get to an 8 or 9. I think we're going to need to go on the moon fairly quickly to do some truthing.
Hmm.
What is it like at 5 centimeters in depth and things like that. The extraction process, there's ways we believe we can extract it with fairly little energy and fairly little moving parts. So I think it will be a stepwise progression. But I do want to say, as we look at this, I think the primary focus is going to be on quantum computing. It requires less helium-3, and quantum computing is going to potentially be a politically strong driver in national security. And learning how to extract a ton is going to solve a lot of the quantum computing needs. And that might bring us to a TR level 8. And then we can start expanding the whole process out for fusion. But I will add one other thing, that beyond at the symposium in November that you guys hosted, it was brought up that we are now in a space race with China. There's no doubt about it. It was brought up. It was brought up in the discussion about the first footprint on the moon, though. I would argue that the space race with China may not just be for that, it might be for this particular substance.
Well, I think
Can I interject a little bit?
absolutely.
Chris brought up a very good point of TRLs and such and operating on the lunar surface. I'd like to point out to everybody in the audience that, from an experience perspective, we have, several days of operation on the lunar surface from Apollo missions. Some countries, such as Russia and China, have operated rovers for extended periods of time. So dealing with lunar regolith, getting back to the lunar surface and just remembering all the technical issues associated with day-night cycles, vacuum operations, abrasive materials, is on its own, irrespective of trying to mine helium-3 or other aspects, are huge challenges. And so, from my perspective, again, I'm a government agent, and I've been working on the technologies and the operations. We are literally in the crawling stage of, or as I like to say, literally trying to scratch the surface of the moon. And when we talk about helium-3, recognize we're talking the 3 to 50 parts per billion range. And so the amount of material that you have to process is going to be staggering to get a product. So, not being a commercial operator, I'm of the learn, progress, evolve stage. The more we can do that, the faster we can do that, is better for all operations on the lunar surface.
Well, I think that's appropriate to bring in Tim Cash's comment from the chat field, where he says that we really need a ISRU laboratory on the lunar surface that really can be examining the components in real time with real scientists and understanding the full scope of what is there. I do recall that the Intuitive Machines is going to be sending a lander to the lunar pole that is going to have a penetrator that is
A
going
drill.
to a drill.
It's an
That's
auger drill and a mass spectrometer.
yeah.
It will be the first time we've drilled on the lunar surface since Apollo.
Hmm.
It's 1 meter deep. It will take several bites, as they call it, of material and bring it to the surface and evaluate it by brushing it and seeing what volatiles come off.
Hmm.
So it's a great first step.
Yeah.
We're going to learn a lot and remember a lot. The generation developing this hardware is much different than the generation that I was I was still quite young during Apollo, but I do remember those missions.
Yeah.
I'm going to add to one thing Jerry said, which is very, very important. He mentioned the parts about 1 part, 2 part, 3 part per billion, who's equivalent of how many parts per billion. Using a normal Earth-based mining technique of extracting it from the ground, putting it through a processing plant, whether it's in a rover or in a centralized place, and spitting the tailings out the back end is going to be massively energy intensive and probably doesn't equate. So to that point, that's really part of the process where going to the moon to extract it is you got to work with the environment of the moon. There's no doubt about it. And you got to understand it's 1 part per billion. That's a really important point he brought up. The other one I brought up in addition was the regolith of the dirt is not like Earth-based dirt. And so the equipment is going to be harmed dramatically. Look at Harrison Schmidt's boot, 22 hours on the moon, probably a third of it was eroded through. So there's a fair amount of challenges, but the ultimate thing is you got to understand the moon's environment or we're going to have a problem. We can go there all day long, but I don't think we're going to bring helium-3 and put it into a processing plant or the regolith to extract it. It's just my humble opinion about that concentration.
Well, I want to come back to this, but I do want to pull Ahmed into the conversation a bit. And, you're looking at fusion, right? And feedstocks, I guess, or fuel stocks for fusion. And helium-3 is being that potential. Um, do you think that accessing larger quantities of helium-3, say from the moon, would help to drive the evolution or the development of that technology? We know that a lot of private money, we understand, is being invested into that, and maybe there's. And I also want you to speak to the time horizon. I
Yeah.
think Chris was kind of bullish as to when these fusion reactors are going to be online versus your attitude about that. So I wonder
Right,
if you
right.
could comment on all that.
So thank you. Yeah, no, yeah, we're looking at the fuel. So to get to your question, I mean, thanks, Chris, also for talking about the fusion 2.0. That's how I look at helium-3 fuel for the helium-3 fusion. So I would say you can look at, we first probably going to get DT fusion, right? And we're going to be all ecstatic about it. And then it's going to open up the path to the helium-3 because it's less neutron. I'm not sure it would accelerate because there's work being done. There are 2 companies, people ask on the chat, there are 2 companies doing the helium-3. They are not tokamak based, which is the conventional one, or IFE inertial base. It's like basically FRC, which is field reverse configuration. And there are 2 companies Helion that's looking at it. There's also Princeton Fusion Systems based in Princeton here. They're both looking at using helium-3, one for propulsion, the other one for producing electricity. And Helion has done a PF, an agreement with Microsoft to produce electricity in a few years. So I just think that the sheer quantity that's going to be required down the road, we have to start thinking about it. And like Jerry mentioned, we are crawling to find out how to get a helium and all that. I think the helium-3 is at that phase. I mean, there are promises. We hope to see fusion very soon with the helium-3, but I'm not sure that's going to be the driver. But once we have it, we don't want to just have a fusion achieved and then say, hey, where do we get the fuel now? And start panicking, right? So I feel like the first step, helium-3 for quantum and also detection for the homeland security. There's a few low requirement, less quantity requirement for helium-3 that might drive scaling up things in the future, 10 years perhaps, in quantity. So I feel like you got to start somewhere. And we, as Fusion, we look at, we're there. Once we know that it can be produced, I think it's going to build confidence for people to start going looking at the helium-3 as a potential fusion fuel in the future. So when in Horizon, it's hard to say. Some companies said in 3 years. I think that it could be 10 years, 15 years, but I think there's a lot of effort in it because the benefit operationally are really could be a game changer.
You could bring
Go
up.
ahead, Chris.
I could add to Ahmed's comment about again. I think quantum and detection and cure. Going back to fusion briefly, tritium is not going to be a walk in the park either, because sourcing tritium, it comes from nuclear fission or the potential of breeding it in blankets that surround fusion reactors, which is still quasi theoretical. So there's a possibility, even with tritium, they may not be able to get quantity. It's an interesting. I mean, it's great that people are advancing the technology, but there's also these restrictions that don't get discussed that often in the press.
That's correct. I mean, from what I recall, the 40 kilogram of tritium that's required, you get about 10 kilograms that's required to start up a fusion plant. I mean, the beauty with DT is you can breed it down the road, right? So it would take time, right? And you start breeding your tritium. So you can imagine that in 2035, when we have the first DT plant, you would have a major dip in tritium because you're going to consume everything that exists, and then you have to rebuild it. But I agree with Chris. They both have the challenges in terms of fuel supply.
There's so many great questions popping up. Let's talk about space law for a minute. I mean, Chris, you'd like to go to the moon. You'd like to access the materials there. Are you giving thought to the impact on, how that would relate to international space law? Obviously, you're going to be, potentially, operating on a very, very wide area to get the kind of concentration that you're going to need. What's your look into that, and have you even been addressing that question?
Well, I might throw it back at you in a minute after I answer, because that's what Beyond Earth does, is looking at policy. But it would be interesting if to put in perspective, it's the opposite of the Antarctica Treaty, where back in the 50s and 60s, all the major players were working more in unison and signed on to protect Antarctica, and you can't even drop a candy bar there, which is great. It's pristine. But on the moon, there's really nothing except for military parameters that define what you can or can't do. In fact, when Trump was in office last time, I believe he signed some orders that basically open up the moon to mining. So I don't think there's anything holding anybody back going to the moon to mine it and to extract it. It's probably, and I don't frankly see, to be frank about it, China, the United States, and Russia and India getting together and coming up with realistic rules about it. But I would turn it back to you because you're more on the policy side.
Well, yeah, no, it is an open question. The United States has passed a law that says that that we are not violating. You would not be violating international space law or the Outer Space Treaty if you were to access the resources of the lunar surface or asteroids and remove those materials with the understanding that you did not own any part of the surface or the asteroid itself, but you could extract materials. Not everyone in the international community agrees with that, so I think that there's still going to be a lot of negotiating going on as well.
Yeah, and I'm not an expert on space law, but I have been lucky enough to work with a number of folks, like I mentioned, in the State Department and NASA legal office that are working to clarify, I would say. And as I put in the chat, it's more of a, how do you interpret the Outer Space Treaty and certain provisions associated with due regard and ownership and things like that. One of the things that an analogy that was mentioned that stuck with me was, like the ocean and fishing. Nobody owns the ocean past certain territorial aspects. So you don't own the ocean, but if you fish and you collect them, you can sell them. So that analogy might exist, and there are rules to, to some extent, to prevent people from, fishing and bothering each other and whatnot. So I think, and again, I'm not an expert. The Artemis Accords, the different, several countries have signed their own laws stating that it is legal to do these things. But I would hesitate to do commercial operations without some level of international agreement, of at least cognizance that yes, we think that we can do these things, and not set off tremendous disputes and such.
Yeah, and we would hope that by the time we're at a point where folks are seriously thinking about or able to do serious mining, whatever that nature might be, that some of these terms would be, and norms would be, readily agreed, whether it's through the
Yep.
Artemis Accords or other mechanisms. And you're right, that is certainly one of the things, one of the areas Beyond Earth is really taking a hard look at. I want
Well, and one other point to kind of bring up here is the idea that, that crawl, I mentioned about crawling and we're working our way. These are the perfect analogies to start using to help develop laws. So nobody in their right mind wants to over legislate and create laws that or legal aspects that would hinder anything downstream. So to some extent, the philosophy that as you're developing technologies and testing them on the moon and evolving your capabilities, simultaneously you start working on those things that help provide the data for those kind of aspects. How much interference does it, how much dust do you loft while you're mining, and will that impact somebody downstream? What type of environmental monitoring aspects do you want to have? How much surface area do you really need to be economical to prevent somebody from, not mining right next to you once you found your whatever resource that you're trying to extract? So those are the things that I think are worthwhile to do simultaneously as we're doing the fun tech stuff that I work on.
Well said. And I think our perspective is, if we do seek to implement some sort of norms in advance, they're only there to help to potentially accelerate the process of moving forward in space. That would make it easier for all parties to feel more comfortable in engaging in these commercial ventures. Let's shift back there. Gosh, there's just so many questions here. Let's shift back to someone was asking about transportation. To what extent is transportation going to be a challenge, just getting to and from the moon, the sort of the highway? Now, I know we have a lot of expectations on the Starship, but Chris, what's your take on that, and hopes and expectations?
I would draw maybe some parallels to what happened to low Earth orbit 20, 30 years ago. Is roughly $10,000 to $20,000 a kilo with non-reusable rockets. It should at some point drop below $100 a kilo with reusable rockets, as the cadence has picked up dramatically. They've barely been on the surface of the moon now. So to Jerry's point, we're at the beginning of that. Maybe it's 20, 30 years from now, in which the cadence picks up so much that it's all reusable. The cost of transportation is going to drop down dramatically. So I really like the low Earth orbit is almost a building block in what actually took place there. It's so different now that it's not $20,000 a kilo.
Mm-hmm. Yeah.
Well, and I think in the chat I made a point that, there's a lot of emphasis going on about Starship and obviously Blue Origin's landers and huge amounts of payload that need to be sent to the moon to establish these kind of things. But interestingly enough, for the product to come back to Earth, you're probably, if you're in the 1 to 10 kilogram-ish range of an initial product to start demonstrating the viability of delivering lunar helium-3, say, to the Earth's surface. Some of the technology is being developed for things such as sample return. Could be viable for some of these early demonstrations.
Okay.
And let's also add one other thing, not to be just purely about the US, but China is challenges. They are suggesting they will be on the surface of the moon in the next 3 to 5 years. India has launched, it has or is launching a human program with one of their goals is to go to the surface of the moon within 10 years. So we have a couple other countries, in addition to a couple companies, looking at transport to the moon. Ultimately, the question is, why are we going back? If we're just going to go back to do research, to look for water after what happened to Apollo, we should be very careful about that. The Apollo lessons learned, there was supposed to have been 20 Apollo missions back in the 60s and 70s. That was before TikTok, cell phones, iPhones, you name it. It was all focused on TV. The world's public was totally glued to their TV sets, and everybody watched the first couple landings. But after 2 or 3, by the time they got to the 6th one, people sort of tuned away. They lost their funding, and I think we should keep what happened to Apollo in mind when it comes to going to the moon, and ultimately ask ourselves, why are we going there?
Yeah. No. That's a good point. I mean, obviously, certainly we want to go back to the moon, not just to plant flags and footprints. That we want to do meaningful things there, and certainly accessing the resources there are an important driver. I'm scanning the questions. Here's an interesting one. This is just talking about the sheer land area on the surface for meaningful mining of helium-3. Have you done, Chris? Have you done some analysis or calculations on sheer acreage that you would require? And Jerry,
Yeah, we actually did a back of the envelope calculation, and it was, I want to say it was about 6 square kilometers to come up with like 200 kilograms for one reactor. But it's not like massive amounts. Now, the other thing that's going to come into play is the depth of helium-3. That's very, very speculative. We are speculating a lot of it's closer to the surface due to solar wind for the past couple billion years. So if it's the people have talked about 1 million tons of helium-3. That's based on helium-3 being almost universally at depth for a couple meters, but if it's more at the surface, it may be less. So I think there's so much speculation. Is it at the highlands more? Is it the Maria more? I believe it's probably at the equator more than it is closer to the poles, just because of where the sun goes. Is it attached to illuminite? Is it is 80% within 5 centimeters, or is 80% within 2 meters?
Those are good questions, and a lot more work is needed.
Yeah.
And to what Jerry just said, I mean, a lot of work is needed on the ground to truth it out, to figure out. You wouldn't go, one of our professors from University of Arizona is on the chat right now. You wouldn't go to any old random place to plop down a copper mine. You want to find where you think your lowest hanging fruit is.
Yes.
It's interesting. Interesting moving to sort of the quantities and really the competition that you pose for existing companies that are providing helium-3, like Air Liquide or Air Gas, Linde, Isoflex. Someone in the chat field has a very a very good knowledge of these providers. How disruptive do you anticipate this being? I mean, is it a complete game changer, or is it just going to be another source that's going to compete with terrestrial sources? And if Chris or
Talking about the
I,
hmm?
I think it should be disruptive. You know, the quantity on Earth here terrestrially are not that on par. I mean, like sub 1 part per billion, if I recall right. So I think, you know, you go 10x, which is what we do at RFIE. We try to look for the disruptive technology, and that falls under that category, I would say, trying to figure out ways to get there. But I'd like to go back to a fact about the moon, all the where do we find it, and in terms of modeling that could be developed to be able to see if it can be scalable. So we don't know how deep we're going to get helium-3 in the moon. So it'd be nice to kind of develop models. So there should be in any kind of mission, there should be like a little science-based mission too to try to develop a model so that we can extrapolate much quickly. Otherwise, it's going to be a group of people go in one place and then, okay, drawing some conclusion based on that, and being able to extrapolate would be good. Another thing that I have not, I mean, during the discussion, I realized ARPA-E could help also would be try to find novel material that could be resistant to this aggressive regolith, right? You would need all the material that we develop here on Earth to go to the moon and deal with the aggressive nature of regolith. So I feel like this is really the land for material science to figure out how do we develop material that will be immune to it. This, to me, I feel is a white space, right? It's worth exploring. Anyway, that's my interjection here. Thanks.
I want to add what Ahmad.
So I want to bring up 2 points that I think you and Chris have already talked about a little bit. One is disruptive. So I look at helium-3 coming back to the Earth disruptive in the fact that not the amount, but just the fact that when it has occurred, what the mindset will change. And I remember, you know, early work on electric propulsion thrusters. Everybody proposed it, but nobody would put it on a mission. Deep Space One happened where they finally put an electric thruster on a mission, and it was only possible with that electric propulsion system. It operated great. After that, everybody was proposing, you know, missions with electric thrusters. I think the fact of doing something on the moon, creating a product and bringing it back to Earth would change the market philosophy. It could change investment strategies, whatever the case may be. The other thing I want to bring up, and I specifically put this in one of my charts, was that the current objectives that STMD and NASA has for ISRU development are based on Artemis pull and Artemis utilization. And so I think the country in general needs to, I'm not a policy person, but it would be interesting to see what the influence of industry-led commercial activities should be on NASA versus government-led activities. And I think helium-3 is the primary example of that change, that if it's up to NASA, you know, we are developing capabilities, as I said, we try to put our priorities together. What are the resources? What are the commodities that will have the biggest influence on human exploration and sustained surface operations? Helium-3 doesn't fit into that picture, whether it's resource exploration aspects or mining for that matter. That said, if part of the US space policy is to advance commercial space activities, one would think, well, okay, that should be an important aspect. So I think, you know, a bigger dialogue about space policy and directions probably should or needs to occur depending on the viability of this helium-3 mining going forward.
I'd like to add to what Jerry said, or maybe even ask him because he works at NASA. But if you take a step back and look at the whole Artemis and going to the South Pole, that's not something that happened in the last year or two. It's probably been, what, a couple decades in the works, and helium-3 probably wasn't even in the equation back then. So it's almost to me like it's a big cruise ship, and if you're going to change the direction of the cruise ship, it's going to take a little bit of time to make that turn so you don't hit the iceberg. So
Yes. So yeah, I really got involved in lunar ISRU during during Constellation. So, 2004 to 2010, we did significant amounts of work on Mare-based lunar regolith, but towards the end of Constellation, there was a big push to go to the poles. We then swung to go to Mars, ignored the moon for a period of time. About 2019-ish timeframe, the moon came back into vogue. And as you mentioned, South Pole seemed to be the logical location for science, for ISRU, for the thermal environment and lighting and conditions, things like that. So you're right. Whether it's a cruise ship or an aircraft carrier, your choice of steering it does take time.
And can I wait one more comment? I don't mean to monopolize this, but the two of you guys said something that's collectively very interesting. 1 minute we were going to the moon, then we're going to Mars. If you look back at what Gene Cernan said 50-something years ago, he said it at some point. We could do all sorts of things on the moon, but unless we solve the dust issue, we're not going to sustain ourselves. And that lesson, or that's haunting from the past, because we haven't solved the dust issue. It's only been recently there's been discussions about mitigation of dust on equipment with coatings or magnets, or electrically charge the surfaces of the properties, let alone
the next CLIPS mission will actually have an electrostatic dust shield on it. So
no, let me challenge you with this one on the NASA side. Inside the habitats, I ain't going to hypothesize there's no way to keep all the dust out. And what it's going to happen.
I won't argue, but with that, that is outside my current work area. But yeah, dust will get everywhere.
Yeah.
And inside the human
is you're setting yourself up for failure.
We've actually the only side trip our company's taken is to look at mitigation of dust for the human in a habitat. It's going to get inside. They're going to breathe it. It's very, very, very dangerous stuff. It can cross. If you breathe in the really, really tiny particles, they don't even get stuck in your lung. It goes right from your lung into your blood, into your brain. So not to scare anybody, but unless we solve that problem too, we have to have astronauts on the moon probably to maintain equipment. It's probably not practical to think it's going to be totally robotic. So there was a little side trip about the dust and what we heard from the past from the Apollo astronauts, and we haven't taken the time to fix it because we're on the process of going to Mars for the longest time.
Yeah, no.
Well, like I said, my career has been, bouncing back and forth between the two destinations. So, luckily some of us that have been around for long enough remember the last iteration and just restart.
Well, yeah, and I think that there may be more than, we have the orbital debris issue, which is also existential. There's certain key problems that have to be resolved if we're going to, get to the moon, develop the moon, and also particularly for human habitation that Beyond Earth is particularly interested in. Let me see if we can get to a couple more questions before we end the hour. Or before we end the program. So Soraya Fisher, she is going back to talking about infrastructure objectives of NASA's Moon and Mars are related to construction, manufacturing, ISRU, and capabilities for leveraging lunar resources, of course, including helium-3. Those capabilities aren't required for the first few Artemis missions, but they are needed for the Moon to Mars objectives, of course, and they will take years to develop. So, Jerry, for you, what do you think that we should be doing now to make sure that those capabilities are needed?
So I kind of wrote something up in the chat, but basically, as I said, we got to get experience. We have to start flying hardware, and doing those iterative lessons learned. Um, so I've always been a very big advocate of progressing in size and complexity of demonstrations, not just assuming I can go full bore production systems the first time. The other is, we need to develop technologies well in advance of when supposedly we're going to need them. And so you look at the Artemis campaign starts with hey, return to, human lunar return, HLR. Then they go into a foundational exploration period where they're sending astronauts, doing EVAs, adding capabilities to stay there a little bit longer over time. The fun really doesn't exist until the sustained lunar evolution phase, where we try to stay there continuously and build up infrastructure. If we wait until the sustained lunar evolution phase to do these things, it's too late.
Mm-hmm.
So while we're doing these initial tests of just getting astronauts back to the moon, remembering how to drive a rover, and not have our spacesuits degrade in 3 days of operations, we should be doing these things. I like to say that every other piece of hardware that NASA sends to the moon wants to avoid regolith. We need to embrace it. We need to live with this stuff.
Mm-hmm.
And so the sooner we start doing that kind of work, the better.
Yeah. Well, this has been such a fascinating conversation. You guys are very, very, very clear-eyed on what's ahead and what the capabilities are. And I gotta wonder, Chris, you're stepping into this as a business proposition. And I can't help thinking that it's still a little early in the game to be putting together a business model around helium-3 extraction from the moon. Could you enlighten us a little bit more on why you feel bullish that that we're ready to take this step right now?
That's a good question, and I think maybe Jerry talked about this a little bit, but I'll give it a different spin. I think, and Ahmad did too. Fusion is probably a TRL level 6 or 7 or somewhere in that range. Extraction of helium-3 is 2 or 3 at this point. So in some respects, we're behind, and we have to do it in parallel. If we wait until fusion's up and running and quantum computing's up and running, this isn't going to take place overnight. So our company's basically focused on theoretically detection, not evaporation, but extraction of it and concentration back into a liquid form. Just these steps, we know we're going to have to partner with all sorts of companies to provide the hardware, the EVA suits. So this is going to take an army of people and potentially a number of countries to get to the moon to do it. But I think we're almost behind schedule in some respects.
Chris, do you think, I know that you have a proprietary technology, if I recall correctly, for actually extracting the material, the helium-3, if I'm not mistaken, if I recall correctly. Is it your hope, sort of short of actually harvesting helium-3, perhaps partnering with NASA to help them in their scientific research or I should say prospecting of what materials are available and so forth? Is that part of your or maybe another way of putting it is, what is your shorter term prospects for potentially revenue generating, to be quite forward about that?
Sure. In the near term, there is no revenue generation at the present moment. We've been in isolation working on the TRL level 2 and getting as much kind of understood and embracing the environment, as I think you mentioned. We are now beginning to look for strategic partners. But my first slide basically said, helium-3 extraction is probably the tip of the spear of a lunar economy. Well, the lunar economy is not just the extraction. You're going to need people to transport, to provide the outer body of the rover, the telecommunications, the food, all that stuff needs to all kind of come together. So we are focused specifically on how to extract with the least amount of moving parts using a low energy process, which is basically embracing the environment. But we're never going to be able to do this on our own. It's going to require more cash now and strategic partners. And any
So I
event,
like what Chris said.
Let me ask
And
you. Okay.
I do want to chime in just for a second. I'm an engineer and I work for the government, so anything I say about business should be considered suspect from the beginning. But I will say, along what Chris was saying, it is the only product from Lunar Resources that has a very clear and near-term market that already exists. You can buy helium-3. It's on Earth, but it's a commodity that is limited and in high demand. The other aspect is it's incredibly aspirational in the fact that there are so many challenges, and I've raised them, to do this at a very large scale that it causes you to build through all those steps that need to be done anyway, to some extent, that I've referred to. You got to have the transportation systems, you got to have the infrastructure in place, you got to get into the maintenance and repair strategies. So from my perspective and how we look at it within NASA and the ISRU community, is that these are common challenges. So I don't do one thing versus another. It's not helium-3 versus water mining versus oxygen and metal extraction from regolith. It's making sure what you do is applicable to as many of those as you can. And then, as I mentioned on my first chart, it should be the role of government to enable industry to be successful. So how do we do that? Those are the things that kind of go towards, why, even though it seems, huge and difficult, it is something that should be considered.
It's almost a kind of a Earth-based analogy might be what it was like in the 1800s before the electric light bulb. And you just had oil lamps and candles. And then a couple people on the East Coast, Thomas Edison and his team, had this vision. And within 10, 20 years, the United States was basically illuminated by electricity. And this is kind of...
My analogy that I like to use is actually the xenon market. That if you look at the cost of extracting oxygen and nitrogen from the atmosphere when it was first done, it was extremely expensive. And then the market transferred to argon, and the cost of oxygen and nitrogen went down tremendously. And then the market went to xenon, and now you can buy oxygen for pennies per pound. So it's kind of that same analogy.
There was a pop-up in the chat box. I will stand corrected because I don't quite know whether it was Tesla or Edison or who stole what from who when it comes to the electric light.
There's a movie on that one.
But I use that in the broader scope that 1 minute we have candles and the next minute we have incandescent lights and that sort of stuff.
Well, Jerry, I think you also bring up, it's such an important point. You're trying to create these capabilities that could be used for many applications, obviously the various resources, the resource elements on the moon themselves, but also actually just getting to and from the moon to do other kinds of things, whether, tourism and other cool stuff like that. But I do think that if there's a driver, right, if there's like one thing that maybe seems the most promising element above all else, and maybe that's helium, that could then be an accelerator Yeah. And I do wonder, and I guess I asked the question, is it really is it really about money? Is the government investing enough, and are their programs aggressive enough? And should there be more of a commercial, is there enough commercial participation as well in that at this particular stage of the game? Jerry?
I'm sorry. I don't advocate the single thing, the killer app per
Yeah,
se,
that's yeah.
um, because I'm always surprised somewhere down the road that something else pops up. So whether it's water in permanently shadowed craters that will change the game because of the locations and what you can do with the water, is it helium-3 that will enable commercial access back to the Earth? People have brought up rare earth elements as oh, we got to get those as well, and stake our claim to those resources on the moon. Um, my career with NASA is within an arm's reach of coming to an end. As I mentioned, I've worked for 40 years. I'm 62, so how many more years I do this? So my approach has been, raise all the boats, or whatever that expression is. The tide raises all boats. So what I'm trying to do with our programs is to do that.
Yeah. Well, that's an interesting way of putting it, the killer app. So, Chris and Ahmed, would you say that helium-3, would you disagree with Jerry and say that maybe helium-3 is the killer app for lunar development?
No, I won't disagree. I think I concur with Jerry, especially for fusion. If fusion gets there, the quantity required, quantum, yeah, absolutely. I think that someone else posted other sources of helium-3. I think it's also something that we're going to look at, but I think that's more down the road because, I mean, 9 years to go to Uranus to be able to get like helium-3, that could be challenging. But I can see helium-3 could be catalyzing the killer app, the fusion, but also fusion down the road can just morph into, I mean, can go to propulsion. So you can have fusion propulsion, which would allow you to go further away in a much lesser time. So I just want to close with that saying that, yes, helium-3 could be the catalyzer and the killer app for everything else.
And Chris, your opinion on that?
I agree, and not to be funny about it, but to me, I'm going to get probably yelled at about this one. To me, the moon is our grocery store. It's sitting there. It came from Earth. Why not use that resource? But on a more altruistic level, if you believe that there's human production of greenhouse gases, I'm not sure if the audience knows this. I just looked this up recently. The amount of CO2 that's produced per year could fill 10 million swimming pools, 10 million Olympic-sized swimming pools. So if anything, if fusion, we can bring enough helium-3 back to make fusion realistic as a greenhouse protector. That altruistic reason is pretty cool. And I also think from a business point of view, has been brought up, this is potentially positive return on investment, probably with the government helping us at the beginning, but at some point, this might be the reason we're going back and forth, back and forth. And then as you pointed out, that might be the driver for maybe people want to go up there and spend some time as a tourist up there, but that's not going to happen without this as the primary driver.
Right, right, right.
Well, I think that's we're actually right at the hour, at the half hour, or the end of the program. So I think that is a good place for us to conclude. I will give, if any of you want to make a last statement, I certainly want to give you a chance to do that.
So I will say
No?
thank you very much for inviting me to this panel. This has been
Yeah.
enlightening to me in terms of like the different, what's required to get this going.
Hmm.
But before I go, I just want to address one comment from Eric that has Eric Reiner in the chat that talks about helium, how helium is going to get helium-3. I mean, this is a big challenge. The claim is to do DD to deuterium to get helium-3. but it's not a slam dunk. So having something to start up would probably require helium from somewhere else. And then after that, once they get things mature, they could do DD. But yeah, it's a valid point. Thank you.
Well, thank you, Ahmed. I want to thank the audience. You have been really flooding the chat field. Really appreciate that. I do want to call in Courtney here for a moment to sign us off. I'm going to. I don't know if you all noticed there that we did not start the recording when we should have at the very top. I may ask Ahmed and Jerry, I think, to re-record your openings. Maybe not right now, but at a time that's convenient for you, because we do want to post this if that's okay.
Well,
But
I sent you my presentation, so just post that. I'd rather not go through another cycle of actually presenting it,
okay,
if that's
fair
okay.
enough. That's fair enough. Yeah, that's fair enough. And then so with that, thank you all. Thanks for the audience. And we'll let Courtney Stad close us out. Why don't you bring
Thank you.
Courtney in?
All right. Thank you all. Very enlightening, very productive. You could tell by the very active inputs, comments, questions from the audience that the hour and a half went by very, very quickly. Is my audio coming through, Steve?
Yeah, you sound good.
All right, terrific. I want to make one comment. We're a think tank. We're nonpartisan, so this is set in the spirit of a nonpartisan observation. You look at Jerry Saunders, you look at Dr. Diallo, you look at Dr. Savino's backgrounds. By the way, you would get a heavy dose of inferiority complex. They have extraordinarily impressive credentials. I know we're going through this resizing, downsizing of the federal government, but you look at Jerry, Dr. Diallo, and Dr. Savino, who's also had a mix of public service and in entrepreneurship. These are national treasures. And so as you're trying to resize, let's keep in mind that these gentlemen are exemplars of how a country maintains its innovation. They could be employed in any other area and be quite successful, no doubt. But I hope it gives you a sense of why it's in our vested interest to encourage, support, and ensure that we keep that resources brilliance that you saw demonstrated the last hour and a half deployed in these cutting edge areas. So with that, we'll get the recording on, and so you all can go back and look at the highlights of this exciting potential resource on the moon. So with that, thank you all very much for your time this afternoon, and we look forward to having you all back for future webinars. Thank you.